Welcome. Welcome. We'll get started in just a minute or two. Give everybody a chance to get in. Again, we're continuing on with the chapter that involves balancing equation, types of reactions. So we'll be picking up there in just a minute or two. Again, a couple of reminders. Looks like everybody is, but please keep your cameras off if you can. And also, if you have questions, feel free to type them in the chat box as well. And again, I'll get to your questions, even if I maybe have moved past your question. If you type it, I'll go back and obviously try to answer your question. So we'll get started in just a second or so. I think this is about where we left off last time. All right. So again, I hope you had a good break, maybe caught up on some stuff. We're going to continue on lecturing where we left off last time. And last time, just to review, we talked about equations and chemical reactions and balancing equations. So remember that when we balance an equation, it is just the coefficient that changes. So never any of the subscripts or anything like that, just the numbers that come in front of everybody. The goal of balancing equations, again, is to get the same number of elements on each side of the arrow. So if you start with 6 carbons on the left, you should end with 6 carbons on the right. Remember, we don't lose any elements along the way. We just simply rearrange everybody into new compounds. So I think that stuff was pretty straightforward in terms of balancing. So we'll continue on here. So the next thing we're going to talk about really for the rest of this chapter are really different ways that you can classify reactions. And there's kind of different ways to classify reactions. You could even classify the same reaction in a couple of different ways, depending on sort of what you are looking at in terms of that aspect. So the first thing that we're going to talk about is an electrolyte. And an electrolyte is a substance that basically, when it goes into water, will result in a solution that can conduct electricity. And the reason why it's able to conduct electricity is because when it gets dissolved in water, or when it goes into water, it creates all these ions. So it creates these ions that have positive charge, it creates these ions that have negative charge. And it's the presence of those ions that are present that helps sort of complete the circuit, complete the charge, and helps something that is an electrolyte basically conduct electricity. There's several different types of electrolytes. There's a strong electrolyte, which we'll talk about in just a second. There's also weak electrolytes as well. And then there's a third type, which is, I guess, still considered an electrolyte, but it's what's known as a non-electrolyte. So a non-electrolyte is different than an electrolyte in the sense that it will still dissolve, but it will not conduct electricity. And the reason why it will not conduct electricity is because although it will dissolve, it will not create no ions. So no ions are formed. And it really is this lack of ions in that solution, which basically prevents it from sort of being able to conduct electricity. So if you have a non-electrolyte, that does usually mean, for example, it will probably dissolve in something like water, but the resulting solution that you make will basically contain no ions. And because, again, there's no ions, there is basically no electricity that gets conducted. So sometimes these are represented or done in an experiment where you take perhaps electrodes that's hooked up to a light bulb, and you put this electrode that has a light bulb attached to it in some different solutions. And you can kind of tell the type of solution it is by how brightly the light bulb will go off. So if we put an electrode like we have here in this picture that's attached to a light bulb, and we put it into a solution that's a non-electrolyte, again, because the solution here, purple on purple, not a good move, because the solution here has no ions floating around, it's not able to conduct electricity. So what we see is what we see in the picture there. The light bulb pretty much does not go on, it stays off. It will not basically be able to conduct electricity. So obviously no light bulb. Same thing if you took something, for example, like a solid ionic compound, like some solid sodium chloride, and you put those electrodes in it, the light bulb will not go off. It is, again, a non-electrolyte. It's not able to conduct electricity. Another type of electrolyte is a weak electrolyte. And a weak electrolyte, as we will talk about in just a second, does create some ions. So in this solution, although we don't have a lot of ions being created, there is still some ions that are being created. And because those ions are being created, it is able to conduct electricity, as we can see here with the light bulb. And the light bulb here does go on, but it is not super bright. So it's not really super bright. It's able to still conduct electricity because there's some ions in the solution. Those little bit of ions in the solution helps kind of complete the circuit and allows some electricity to be conducted. But again, in terms of the light bulb example, it would give you more of a dim light bulb. And that is different than in a strong electrolyte solution. In a strong electrolyte solution, we pretty much have all ions that are present. So whatever you dissolved in that solution would have 100% broken apart into ions. You have pretty much nothing but ions floating around that solution. Since you have so many ions floating around that solution, obviously that would allow the electricity to be conducted really well. And we can see how bright that light bulb goes off in this picture. So those are sort of three sort of electrolytes. We're going to talk about each of these in just a second, but a strong electrolyte 100% breaks apart into ions. So you have a ton of ions. A weak electrolyte makes a few ions, but mainly stays together. And then our non-electrolyte, as we talked about there, will dissolve in water, but will produce no ions. So in terms of the light bulb example, strong, very bright like we see, weak, kind of a dim light bulb coming off, and a non-electrolyte, the light bulb essentially will not go off. Any questions on that? So again, a reminder, if you do have questions, feel free to type them in the chat box area, and I will answer them even again if I happen to move on to the next slide. I'll go back. So when we talk about a strong electrolyte versus a weak electrolyte, it is, again, really the presence of those ions that help it conduct electricity. So when we have a strong electrolyte like sodium chloride solid, we take that sodium chloride and we put it into water, it is 100% in that solution that you would make be just the sodium ions and the chloride ions floating around. You would have none of the sodium chloride units still together. And again, because it 100% breaks apart into those ions, it conducts electricity very well. So electricity. Kind of that bright light bulb. This, you could almost think about it as a, draw a giant arrow, basically a one-way street heading towards the product side. Nobody is coming back the other way. 100% of what we would have would be our ions. And that is different than what typically happens in a weak electrolyte. Now, in a weak electrolyte, it will dissolve, it will create some ions, but the difference is, and the difference of how you can recognize a weak electrolyte is we will have a reversible reaction. So when we have arrows that head in both directions, this implies a reversible reaction. And basically what that means is there is a forward direction, which goes from reactants to products. And there is a reverse direction that goes from products back to reactants. And when something like this, which by the way is acetic acid, basically your acid and vinegar. So when we take something like acetic acid, which is a weak acid and also a weak electrolyte, what we mainly have in the solution is this guy still together. But it will break apart into these ions and it will produce a few of these ions in solution. So what that essentially means is because it's still able to produce a few of these ions on this side, it will still be able to conduct electricity, but again, nowhere near as good as our strong electrolyte. So it's still able to conduct electricity, but again, nowhere near our strong electrolyte. And again, with the picture that we saw on the other slide, this again would be more the dim light bulb. So light bulb still turns on, but very dim, as opposed to the bright light bulb that we would see up here with our strong electrolyte. Any questions on that there? HF, which is also a weak acid, is also a weak electrolyte. It will break apart into H plus and F minus. And again, in solution, you mainly have this guy together with a little bit of these guys kind of floating around. So again, if you kind of drew what you have in our HF example, we would have a lot of HF still together, but we would also have some F minuses, also have some H pluses from each other, but a majority of what would be in the solution would again be that whole unit together. And as I mentioned before, that is really the key to recognizing that something is a weak electrolyte is you will kind of see those arrows heading in both directions, which again implies it's a reversible reaction. And what that means is in certain cases, the products will come back together to make the reactants, while the reactants will come back together to make the products. At some point, which you'll learn and talk about in whatever class it is, 200B, I guess they call it now. It will reach what is known as usually chemical equilibrium, which means the rate of the forward reaction will equal the rate of the reverse reaction. So when something reaches chemical equilibrium, it doesn't mean necessarily that you have the same amount on both sides. It just means as quickly as it goes to the product side, it will just as quickly go back to the other side, to the reactant side. So it goes back and forth in basically the same rate. And what that essentially does, again, will basically lock everybody into place in terms of their concentrations, and there won't be much changing in terms of their concentrations. So an acetic acid is a weak electrolyte because it is not completely ionized in water. So again, mainly stays together and breaks apart a little bit. Now, the process of hydration is essentially what occurs when we do dissolve something in water. So as we know, water is a polar molecule. The negative side of water is by the oxygen, which is what this guy is. And the positive side of water is down by our hydrogens, which is what these guys are. And that works really well, especially when we take something that's ionic. And when we take something that's ionic and solid and we dissolve it in water, that again is how we get our aqueous guys, which is a positive and negative guy that dissolves in there. So, for example, like our sodium chloride that we saw on the other, when you dissolve it in water, you get sodium ions floating around and you get chloride ions that are floating around. Now, although we kind of write them in formulas with nothing there, what the AQ, which is what this is, AQ, is aqueous. What it essentially means is these ions here are surrounded by water. That's essentially what happens to allow something like sodium chloride to dissolve. It gets surrounded by all these water molecules. It gets surrounded by the negative side of the water molecules. Again, if this was sodium, it has a positive charge. It is going to be attracted to the negative side of water. And that's going to help it basically dissolve. And this is the process known as hydration. While the chloride would be our negative guy, which would be attracted to the positive side of water, which is our hydrogen side. And this process does two things. It allows something like sodium chloride to dissolve. And really the waters here, as you can kind of see in this picture, act almost as a buffer that prevents the positive ion from coming back to the negative ion. And we know what happens when we do something that is a solution of sodium chloride. If you heat it up, what's going to happen is as you heat this guy, nice Bunsen burner picture, basically our water molecules will start to evaporate. And at some point, if you evaporate off all the water molecules, there is nothing there to prevent the negative ion to come together with the positive ion. And that's an extremely strong attractive force between those ions. And they would come together and reform the solid sodium chloride in that case. And these guys, because of that electrostatic attraction, would come together and make that solid sodium chloride. Any questions on that? So this is an example of a non-electrolyte, which obviously something like sugar is an example of a non-electrolyte. If you take something like sugar, a little sugar packet, and you dissolve it in water, as you know, it will dissolve in water. But something like sugar, which is essentially made up of carbons, hydrogens, and oxygens, those are all nonmetals, which means they're going to be doing some type of covalent bonding. And in covalent bonding, what we have is sharing of electrons, and we have no ions that are being formed. So although something like sugar will dissolve and it will become a solution, which again is represented by that aqueous symbol, it will not produce, no ions will be made. And again, because there's no ions, it will not be able to conduct electricity. So here's this table, not from your book, but you probably have a similar one. These are all strong electrolytes. So all these guys in this category 100% break apart into ions and will be very good conductors of electricity. These guys over here are some weak electrolytes, things like hydrofluoric acid, nitrous acid, ammonia, which is a weak base, acetic acid, also a weak electrolyte. When they are in solution, again, they mainly stay together, but will produce a few ions. And again, because they're able to produce a few ions, they will still be able to conduct electricity, but again, not very well. And over here in this last column, we have a lot of things that are going to be covalently bonded. All nonmetals going to produce no ions. And because we produce no ions, will not conduct electricity. There you go. No conduct electricity. That's pretty good, I suppose. Any questions on electrolytes? Okay. So again, so there's this idea of electrolytes are going to be really important, especially when we talk about a certain type of reaction and what occurs in a certain type of reaction. So let's get into sort of these. Now we're going to talk about ways to classify different types of reactions. And really these reactions, they're going to fall under kind of a couple of different umbrellas. And sort of underneath these umbrellas, there will be different ways to classify kind of the same reaction. So really the first sort of big umbrella of reactions is ones that are known as double displacement reactions. So double displacement reactions is sort of the big umbrella in which some other reactions are also there, and they're basically the same thing. And one of those is a precipitation reaction, which we'll talk about here in just a second. But in a double displacement reaction, the way that you could recognize it is pretty simple. You will be starting with not one, but you will be starting with two ionic compounds. So on the reactant side, you will see two ionic compounds, a positive and negative guy. And basically, the classic thing that happens in a double displacement reaction is the two positive guys will switch partners. So A, which is positive, will end up with D, which is negative, to create a new ionic compound. And then our C, which is positive, will end up with B, which is negative, to create another new ionic compound. So in a double displacement reaction, for which a precipitation reaction is part of those type of reactions, you basically get a switch that occurs between the cations and they switch up with the other anions that are present. What makes something a precipitation reaction is, much like the name implies, a PPT, which is the abbreviation for a precipitate. When this switch occurs, usually one of these, could technically be two, but usually one of these will make a solid. And that is how you know that this is a precipitation reaction. So obviously a precipitation reaction would have to make a precipitate that basically is a solid. When we talk about, excuse me, a precipitate that's being made, a precipitate does not have to necessarily be like a rock hard solid that's made that just drops to the bottom of the test tube. It can be something kind of like what we see here in this picture. It can be something that's just kind of gets cloudy. There's some cloudiness that sort of forms that wasn't there before. And that's a good example of a precipitation reaction occurring. And it usually occurs from when you mix a couple of solutions together and some type of solid is made. So for example, if we look at this reaction, this is the reaction that's occurring there on the left. We're going to take some lead to nitrate. We're going to react it with some sodium iodide, and we're going to make lead 2 iodide and sodium nitrate. Now, if you weren't sure what type of reaction this is, when we look at this, this is an ionic compound. That's a positive and negative. This sodium iodide is also a positive and negative. And in this case, what that means is this is your classic double displacement reaction, the way it's sort of set up. The two positive guys are going to switch partners. Now, in this case, you're actually given the formulas on this side. If you were not given the formulas on this side, you want to make sure that you write the correct formula first and then you balance the equation. Very commonly, people will frankly screw up on this by trying to balance the equation and write the chemical formulas at the same time. So the order you want to do if you're not given anything on the product side and you have to predict what will happen on the product side is you just want to look at each of these guys on the reactant side and think about the two things that make it up. So for example, lead 2 nitrate is really made up of a lead with a +2 charge, and it's made up of a nitrate with a -1 charge. Again, I could care less at this point about the two or anything like that. The sodium iodide here is made up of the basic unit of sodium, which is group 1, which is a +1 charge. The iodide is group 7, which is a -1 charge. So if you had to predict what comes on the right-hand side here, you want to just take the basic units and then put them together. So what we're going to do is take the lead and we're going to combine it with our iodide. So that's a +2 and a -1. And that is how we get to the correct formula that we see over here. We need 2 I's to balance out that +2 charge. Same thing when we take our sodium, which is +1, and we put it together with our nitrate, which is -1. We just need one of each of these. And if we put it together, it again will look just like this. Once you write these formulas down, then you could go back and balance it by changing the numbers in front. So you could change the coefficients in front after you get that right formula. And again, in this particular case, we need 2 here and a 2 here. So there will be problems where you'll have to predict the formulas on the product side. That is the order you want to do it. Basic units, put it together with the correct formula, and then balance it. If you try to do both of those things together, which happens a lot, you probably will get an equation that won't balance. You'll have the wrong formulas, and you'll probably get a lot of X's and stuff like that, which you don't want. Any questions on sort of putting that together? Now, when we do see this equation written here, this is a certain type of equation which is known as the molecular equation. And the molecular equation is an equation where we write everything out in terms of their whole formulas, everything together. Now, although this is a formula that does describe the overall reaction that is taking place, it really does not describe what is truly happening in this solution when we mix them together. So remember that when we are talking about a solution, something like our lead 2 nitrate, really in that solution, what we have are lead 2 ions floating around, and we have nitrate ions floating around. We really don't have any of these units still together. So there is another equation that you could write for this type of reaction that will describe what is truly happening sort of in the solution. And this equation is what is known as the total ionic equation. Or some people will call it the complete ionic equation. And that one looks something like this. So just to show you how we got there, the basic unit of lead when it goes into the solution will be lead with a +2 charge. This would also be aqueous. We have a nitrate, but the 2 here comes to the front. So then we get 2 nitrates that are floating around. This 2 that's in the front will distribute to each of the ions when it goes into solution. So that will give us 2 sodium ions and 2 iodide ions. Now, when we come to the other side, we run into our precipitate, which is our solid. So in solution, like you can kind of see in this picture, our precipitate will basically stay together. If it didn't stay together, then it would be ions. So when you write a total ionic equation, anything that is a solid or a liquid, you keep together. So that is why here we did not break apart our lead 2 iodide, because that again is a solid and would be kept together. When we come to our sodium nitrate, the sodium will break apart into ions. We'll get 2 sodiums, again, distributing that 2 in front, and we will get 2 nitrates. This again is what is sometimes referred to as the total ionic equation or complete ionic equation. It is an equation where we break apart any really strong electrolytes into their ions. We keep together solids and liquids. And the other thing that if you should come across it in a total ionic equation is we keep together weak electrolytes. So like we were just talking about. So if you come across something that is a weak electrolyte and you go to write the total ionic equation, you should keep it together. So those are really the 3 things that, you know, if you see in an equation and you want to go and write a total ionic equation that you should keep together, anything that's a weak electrolyte, anything that's a solid, anything that is a liquid, a pure liquid, and really, I guess we could add one more to that. It does pop up occasionally. Anything that's a gas. Yeah. So anything that's a gas will also stay together because it's most likely going to be a covalent compound and will not break apart into ions. So occasionally gases will pop in there. And our weak electrolytes, though, will be things that do have the aqueous symbol next to it. But if you can identify it, something like acetic acid, the hydrofluoric acid, you technically would keep those together. So although we have this total ionic equation, which describes what is truly happening in that beaker, in that test tube, we can actually look at the total ionic equation, and you will typically be able to find ions that are present on both sides of the arrow that look exactly the same. So in this particular case, if we look on the left-hand side of the arrow, we have 2 nitrates. And that looks exactly the same as our 2 nitrates that we see over here. We also will see 2 sodiums on the left-hand side of the arrow, which look exactly like our 2 sodium ions on the right-hand side of the arrow. And typically, if you do this correctly, you should have the exact same number of ions on both sides. So what I mean is we have 2 nitrates on the left. We should have 2 nitrates on the right. We have 2 sodiums on the left. We probably should have 2 sodiums on the right. These ions that look exactly the same on both sides, we can typically cross them out because they are what are known as spectator ions. So these are spectator ions. And much like the name implies, our spectator ions are pretty much just there watching. They are really not involved in the actual product that's being made in this reaction. So if you look at that test tube to the left, the actual product that's being made is that yellow solid, which is the lead 2 iodide. So we typically will cross out our spectator ions. And what we're left with is this last type of equation that we see here. This is what is known as the net ionic equation. This is the equation that you get after you cross out all your spectator ions. It is truly the equation that describes what is happening in this reaction. Although we're mixing together lead 2 nitrate with sodium iodide, what is truly happening when you mix those 2 solutions together, which by the way is clear solutions, no solid or anything like that. What is truly happening is the lead 2 from the lead 2 nitrate is coming together with the iodide from the sodium iodide, and that is truly what is coming together to form our precipitate in this reaction. So you can kind of think of the net ionic equation as kind of the basic bare bones of what is happening in this reaction This is actually overall the two things that are coming together to form our product. So that is the molecular equation, which we write everything like normal with our correct chemical formulas. The total ionic equation, we break apart anything that can be broken apart. We keep together solids, liquids, and weak electrolytes. And then we get rid of our spectator ions, and we're left with what is known as the net ionic equation, which basically describes what is happening in this reaction. Any questions on that? So these are the steps to follow to sort of write a net ionic equation. So for example, if we have this reaction here, we want to write the net ionic equation for the reaction of silver nitrate with sodium chloride. So the first thing that you want to do is, again, start with the molecular equation. So if we start with the molecular equation, we're starting with silver nitrate, which is this. We're going to react it with sodium chloride, which is this guy. And again, this is a double displacement reaction. We have our positive, negative. We have our positive and negative. So again, what's going to happen is our two positive guys are going to switch partners. So the silver is going to come over to our chloride, and our sodium will come over to our nitrate. So again, we want to put this together with the correct formulas first. So silver is +1 and chloride is -1. So when we put that together, we get silver chloride, and that is going to be a solid. And when we put the sodium, which is +1, together with the nitrate, which is -1, we will get sodium nitrate, which looks something like this. And this would be aqueous. We're going to talk about in just a second how we know this is a solid, how we know this is aqueous. We'll get to that in just 1 second. This is what will represent our molecular equation. We do want to make sure it's balanced. So if we look at it, we have one silver on each side. We have one nitrate on each side, one sodium, and one chloride. So it is balanced. We then can write our total ionic equation by breaking it apart. So the silver nitrate will break apart into silver ion and the nitrate ion. So this will break apart here into silver with a +1 charge, plus our nitrate with a -1 charge. The sodium chloride, which is also a strong electrolyte, will break apart into sodium with a +1 charge and chloride with a -1 charge. Now coming to the other side, we have our solid here. So as we talked about, the solid will stay together. So silver chloride will stay together as one unit. This aqueous sodium nitrate, also a strong electrolyte, will break apart into sodium ion and the nitrate ion. This again will represent our total ionic equation, our complete ionic equation. And again, this is the equation which represents what is truly happening in that reaction. And it's also the equation that we can look on both sides and try to find ions that look exactly the same. So again, if we look on both sides, we will see that we have a nitrate here, which looks exactly like the nitrate on the other side. We also have a sodium here, which looks exactly like the sodium on the other side. These guys, again, are going to be our spectator ions, which again, they're just kind of hanging out. They're kind of watching what's going on. Truthfully, they're really there just to balance out the charge of everything, but we do cross out our spectator ions. And again, that's going to leave us really the true reaction that's happening. So when we mix these two things, truly what's happening is the silver from the silver nitrate will go find a chloride from the sodium chloride, and those two guys will come together to make silver chloride, which is our solid. And again, this would be our net ionic equation. Any questions on how to get there? Now, this is truly the right way to kind of go about figuring out the net ionic equation, but there is sort of a shortcut way that if you know what the solid product is, you could get the net ionic equation kind of quickly from it and going backwards just from that. So basically, for example, if we knew in this reaction that our solid would be the silver chloride, you would put that on the product side and just go, silver chloride is made up of one silver ion and one chloride ion. So you could kind of work backwards if you know the solid that's being formed. You can even do that with the one we saw previously, which was the lead 2 iodide. That is the yellow solid. Again, if you put that on that side, this is made up of a lead that has a +2 charge, and an iodide which has a -1 charge, but not just one of them. It's made up of two of them. So you can sort of go backwards if you really know what the solid product is and write the net ionic equation without necessarily having to write the molecular equation, the total ionic equation, and then the net ionic equation. So for example, experiment 8 will ask you maybe to do some of that. You can sort of work your way backwards from the actual product. Any questions on that? So again, as I mentioned, there is a way to sort of know or sort of figure out whether or not when we mix these two ions together, will we get a solid? Will we not get a solid? Will it be something that's more of a solution? And again, just a reminder, just so everybody is clear, when we talk about something with the L symbol versus the AQ symbol, the L symbol is a pure liquid. So something like if you just had water by itself, nothing else in there, just pure water, that would be considered a liquid. And again, something like pure water is covalently bonded, so it wouldn't fall apart or anything like that, which is why we don't break it apart. That is different than something that is basically aqueous. Aqueous basically means a solution, which basically means you took something like sodium chloride, that's a solid, and you added it to water, that's a liquid, and that gets you sodium chloride solution. And different than that is you do have water molecules and you do have sodium ions and chloride ions floating around in that solution. So if you talk about something that's L, which is a liquid, it is just one thing by itself. Something that's AQ, which is aqueous, means that you took something and dissolved it in something like water. Doesn't always have to be water, but a lot of times it is water, and you make a solution. Any questions on any of these things? So obviously you do need to be able to write molecular equations correctly. You need to be able to write the total ionic equations, figure out the spectator ions, and then also write the net ionic equations as well. So you may be asking, like, how do I know if something's going to make a solid, something is not going to make a solid? And that's really where solubility rules come into play. So I think if I remember correctly, that's everything I wrote in by hand. In case you want to see it later, we're watching this to help you sleep, whatever it may be. But to help us decide if we are going to get a solid, if we mix a couple of ions, or if we're not going to get a solid, the solubility is what can help us do that. The solubility of something is basically the maximum amount of solute that will dissolve in a given amount of solvent. So when we talk about a solution, which again is that aqueous symbol. Really, a solution is made up of two parts. It's made up of the solute, which is the smaller part of the solution, and it's made up of the solvent, which is the larger part of a solution. So if you take the solute and the solvent, that makes a solution. So if we have something that is a sodium chloride solution, the solute is always the name of the solution. So the solute in this case would be sodium chloride, and the solvent would be water in this case. Yeah. So together they come together and make that aqueous solution. So there is a maximum amount of solid that you could get to dissolve at a given temperature. If the temperature increases, you usually could get more solid to dissolve. If the temperature decreases, you could get less solid to dissolve. But solubility, and really what will help us determine whether or not we do get a solid or not, is what is known as solubility rules. And when we look at these solubility rules, if something is said to be soluble, what that means is when you write the chemical formula in the equation, it will get the AQ symbol next to it. So if something is soluble, it will get the AQ symbol. It means essentially you have a solution. So it will all look the same throughout. You won't see any solid, although I guess this blue kind of looks like solid. We'll just imagine that that's all the same throughout there. Solid or anything like that. If you look at solubility rules and it says that combination is insoluble, that means that those guys with the chemical formulas will get an S next to it to indicate solid, which means when you do it and you mix them together, you'll get some type of solid that will form. I'll just draw it like that. So let's take a look at these solubility rules and sort of see what we are dealing with here. So these are guys that are typically soluble in water. So starting over here on the left-hand side, we have lithium, we have sodium, potassium, and ammonia. This is essentially group 1 on the periodic table. So really group 1 on the periodic table, and ammonium. Again, that's ammonium, not ammonia, ammonium. If you see any of those guys in a chemical formula, it is going to be soluble. And there are no exceptions, which is on this side. So that means as soon as you pretty much see any of those in a formula, you pretty much can lay up the AQ symbol next to it. Also, when we have anything that is nitrate or acetate in a chemical formula, there are no exceptions either, which means as soon as you see one of those guys in a chemical formula, those guys should also be aqueous. Now, if you see chloride, bromide, or iodide in a chemical formula, those guys are going to be soluble. So those guys will get the aqueous symbol. But there are some exceptions over here. And the exceptions are if you have chloride, bromide, or iodide, and it is hooked up with silver, this is mercury 1, and lead 2. So if you have any of those three with chloride, bromide, and iodine, it is opposite of being soluble. It goes from being soluble to being insoluble. So it will become insoluble if you have any one of those three that are hooked up with chloride, bromide, or iodide. Sulfates are also soluble, which means if you see sulfate, you should give it an aqueous symbol. But again, there are some exceptions over here. So if any one of these exceptions are connected or is connected to sulfate, it will go from aqueous to insoluble and get that solid symbol. So there are certain things that are soluble in everything. There's no exception. As soon as you see them in the formula, you know it's going to be aqueous. And there are things that are typically soluble in a lot of things, but there are some exceptions, which then means it goes from being soluble to being insoluble. Any questions on how to use this part of the table before we look at things that are typically insoluble? Again, if you do have questions, please feel free to type them in. I will get to your question even if I happen to have moved on from that slide. All right, so let's take a look at these solubility rules here. Now, these are different. These are the solubility rules for things that are typically insoluble in water. So these are guys that typically will make a solid if they're present. So looking here at hydroxide, hydroxide typically will make a solid, but there are a lot of exceptions. Our exceptions here are the same ones that we saw on the previous slide. That is group 1, and that is ammonia, which means if you have any of these guys hooked up with hydroxide, it will go from being insoluble to being soluble. Barium, strontium, and calcium is what is known as slightly soluble. Sometimes you'll see it in a table like SS, which means slightly soluble. But most people will consider slightly soluble to be more like insoluble. So sometimes you'll see it being more like insoluble, but slightly soluble does mean what it sounds like. A little bit of it will be able to dissolve. Same thing down here. If we have sulfides, it typically will make solids with whatever it's hooked up with. Again, our same sort of exception here are group 1, our ammonium, and also our calcium, strontium, barium. Again, if you have any of these guys hooked up with sulfur, it will go from being insoluble to being soluble on this side. And lastly, carbonates and phosphates are typically insoluble, except for these exceptions here, which again is our group 1 from the periodic table and our ammonium. And again, if you have any of those exceptions, they will go the opposite sort of direction. Any question on those? So this is how, for example, if we look at that earlier equation that we saw, one of them, which was silver nitrate plus sodium chloride makes some silver chloride plus some sodium nitrate. So if you just had those formulas and you wanted to determine, hey, is it solid, is it not solid, this is where you could use your solubility rules to do that. So looking at this first one, although we may not be able to see silver by itself in the table, we can see nitrate. And when we see nitrate, it's right here. It has no exception, which means as soon as we see the nitrate, this guy should get the aqueous symbol. Over here, we have sodium, which is group 1, which is right here. And there's no exceptions either, which means truly that's as far as you need to go. It is going to be aqueous. But in this case, we actually could look at the chloride. If we look at the chloride, it is going to be soluble, except with silver, mercury, or lead, which is not the case. So it also tells us that this thing should be soluble as well. Coming to the other side, we have our silver, which again, we might not be able to find, but we can find our chloride. Again, our chloride is soluble in everything except silver, mercury, and lead. And in this case, it is combined with silver. So it goes from being soluble to being insoluble in this case. And this is how we know the silver chloride is the solid. When we come to our last guy here, we have the sodium, which is really as far as we need to go. Again, no exceptions. So it's going to be aqueous. We could also look at the nitrate as well. No exceptions, going to be aqueous. So this is how we could kind of use solubility rules to help us decide what's going to be a solid, what's not going to be a solid by using these rules here. Again, we could look at our previous one, or one of our previous ones, where we had lead to nitrate plus potassium iodide, makes some PbI2 plus some KNO3. And I guess to do the right thing, do a little bit of balancing, right? So if we look at these guys here, the lead we might not be able to find, but again, on the previous slide, the nitrate, there are no exceptions. So we know that is going to be aqueous. When we look at the next guy, we have potassium, which is group 1. There are no exceptions, so it's going to be aqueous. The iodide is soluble in everything except for silver, lead, and mercury. And in this case, it's attached to lead, which means it goes from being soluble to being insoluble. So this would be our solid that we would make. Here, potassium is soluble in everything. Nitrate is also soluble in everything. And that is how we would know that we would have the aqueous one here. So by using these solubility rules, it will allow you to determine, which one is the solid and which one is aqueous. Any questions on how to use the solubility rules here? You should be familiar with the solubility rules. They probably will be provided for you, but I think you should have some familiarity with the solubility rules. So if we look at some of these examples here to see which ones would be soluble in water and which ones might not be so soluble in water, let's take a looky here. We look at potassium hydroxide, and really, that is as far as you need to go. Potassium is group 1, which means it's soluble in everything. There's no exception, which means we would expect this to be soluble because of the potassium. Here we look at silver bromide. Silver we might not be able to find. We can find bromide. It is soluble in everything except silver, lead, and mercury, which in this case, there's the silver, right? So it goes from being soluble to becoming insoluble in this case because of that exception. So we would expect a insoluble product and this guy to become a solid. Any question on those first two? Continuing down, our calcium chloride. Again, may not have to worry about calcium, but as soon as we see chloride, again, we know it's soluble just like the bromine in everything except our silver, lead, and mercury, which in this case, there is none of those. So we would expect calcium chloride to be soluble and get that aqueous symbol next to it. Lead 2 nitrate, as we did in our example, nitrate is as far as we need to go. Nitrate is soluble in everything. There is no exception, which means we should expect this to be soluble. And lastly, we have our sulfate. And our sulfate is going to be insoluble in this case. Get it to come out here. There we go. Again, most sulfates are soluble, but one of the exceptions is our lead 2 sulfate. Any questions on any of those there? Okay. So again, we could use these things to help us write our equations. So why don't you try this one here? Take a minute or two, then we'll go over it. Why don't you write the equation for the precipitation reaction that occurs between potassium carbonate and nickel 2 chloride. So write the molecular equation and see what you come up with. And take a minute or two, then we'll talk about it. Okay, so let's take a look here. So in this one, again, since everything's in words, you want to make sure that you start with obviously the correct formulas. So potassium carbonate from our good nomenclature stuff, right, should look something like that. K2CO3. And we do know that it is going to be aqueous. We already know that because it says a solution, but if we didn't, we see potassium there, and potassium is soluble in everything. Nickel 2 chloride, nickel with a +2 charge, and chloride with a -1 charge will give you something that looks like this. And again, we do know that this is going to be aqueous as well. We have chloride, it's not attached to silver, lead, or mercury. So again, this is our double displacement reaction. We got a positive and negative. So again, the basic unit of this first guy is a potassium with a +1 charge. The basic unit here is carbonate with a -2 charge. The basic unit of this guy is nickel with a +2 charge, which again is what that means. And the basic unit here is chloride with a -1 charge. Again, I'm not going to be concerned at this point with any of these extra twos because I want to just make sure I get the correct formulas on the other side. So in a double displacement reaction, our positive guys will switch partners. So our potassium will come together with our chloride, and our nickel will come together with our carbonate. So when the potassium comes together with the chloride, that is K with a +1 charge, Cl with a -1 charge. The correct formula here is KCl. It is not what a lot of people will write K2Cl2 because of those extra twos. So again, you want to make sure that you get the correct formulas down first. The other thing that will come together is the nickel that now has a +2 charge, the carbonate that has a -2 charge. So what that means is you just need one of each of these guys to put it together. Again, not going to worry about extra of either of those things. In terms of balancing, we do want to make sure it's balanced. So it's at this point, once we got the correct formulas down, we balance it by putting the 2 in front of the correct formula, not like this. Any questions on how to get that formula? Now we could use our solubility rules to help us determine that. Potassium is soluble in everything, so that's pretty much as far as you need to go. Chloride also soluble in everything except for silver, lead, and mercury, which is not the case here. Carbonate is going to be our insoluble product based on our solubility rules. So this again would represent our balanced nuclear equation, maybe a nuclear equation, our balanced molecular equation. And it didn't really ask you to do so in this one, but just for practice here, since we've been talking about it, if we wanted to write our total ionic equation, so this obviously would be our molecular equation. Our total ionic equation here, we would break apart everything that's aqueous. So when we break apart our first guy, we get 2K pluses. The 2 comes out in front. And we get 1 carbonate. When our nickel 2 chloride breaks apart, we get 1 nickel that has a +2 charge. And for the chloride, the 2 comes out in front, and we get 2 chlorides. Coming to our other side, again, aqueous over here, so it's a strong electrolyte. The 2 gets distributed to everybody that's there. And the last thing that we have is our solid, which will remain together, which is our nickel carbonate. This again would represent our total ionic equation. Any questions on that? And again, remember that in our total ionic equation, this is where we can find our spectator ions. We look to the left and we look to the right. We will see two potassiums that look exactly the same. And we will see on the left-hand side two chlorides, which match the two chlorides that we have over here. Again, these guys being our spectator ions. And as we talked about, you could cross out the spectator ions. And what that will leave you is the third type of equation, the nickel plus the carbonate is coming together to form that solid, the nickel 2 carbonate. And this is our net ionic equation. And typically speaking, when you write an equation, much like an ionic formula, positive guy first, then negative guy is usually the way that you write it. Any questions on how we got to any of those three equations? When you write these equations, the total ionic equation, the net ionic equation, in the name for those things, they say this word, ionic, yes, which means you need charges when you write these things, yeah? So as you can see here, charges on the ions need to be written out all the way across, yes, when you write these type of equations. So very common, people also will forget to write the charges when they do a total ionic equation or a net ionic equation. So anything that you write that's an ion by itself should have the charge associated with it. Any questions on that example there? Which is obviously and again, this is a double displacement reaction. And this is also classified as a precipitation reaction because this is the precipitate that was made as a result of this reaction. So again, double displacement and precipitation kind of describes the same reaction, but sort of different aspects of the same reaction. Any questions on that? So I'm just going to scroll through this, which I think is everything I wrote. I think they take a ton of pages to do it, but I'll just scroll through it in case, again, you're watching this to put yourself to sleep later. You can then see it before you fall asleep. Yes. So why don't you try these two here, and then we will talk about it. So take a minute or two and write the balance equation. So for these, we'll just go with just a straight molecular equation for each of these and see what you end up with. So take a minute or so, and then we'll talk about it. All right, so if we look at these, again, you should be able to recognize these as double displacement. We have a positive and negative guy. We have a positive and negative guy. So again, as we were talking about, when we're trying to predict what's on the other side, we want to just take the basic units of these guys. So the basic two things that make up potassium chloride is a potassium with a +1 charge, and it is a chloride with a -1 charge. And for our silver nitrate, same idea. The basic unit of silver nitrate is silver with a +1 charge, and our nitrate with a -1 charge. So because this is a double displacement reaction, as we've been talking about, we're going to basically swap partners here between the positive guys. And again, when we put it together on the right-hand side, we want to do the correct formula. So K plus and NO3 minus, you just need one of each, will get you KNO3. When the silver comes together with the chloride, again, silver being +1 and chloride being -1, you again just need one of each of those guys. And those again would be the correct formulas. At this point, we would want to go back and balance it, which in this case, it actually is balanced. We have one potassium on each side, one Cl on each side, one silver on each side, and one nitrate on each side. So in terms of solubility, we can look at our rules. Again, we see potassium. So that's really as far as we need to go. We can also look at the nitrate, which is also soluble in everything. And we would know that this would be soluble. The chloride here, again, is soluble in everything except silver, lead, and mercury, which in this case, that means it will go from being soluble to being insoluble in this case. And we will get this formula here. Any questions on that? Okay. Now we would do the same approach for our bottom guy. And for our bottom one here, again, it is a double displacement reaction. And we can know that by looking at it. And we got a positive and negative guy. We got a positive and negative guy. Again, the basic unit of sodium is sodium with a +1 charge. The sulfur is a -2 charge. Again, I am not worried about that too at this moment. The basic unit of calcium chloride is calcium with a +2 charge, chloride with a -1 charge. Again, not worried about that as well. We're going to switch partners. So we're going to go this away, and the calcium will come together with the sulfide. And that will give us sodium chloride when we put it together. And one calcium at +2, one sulfur at -2 will give us calcium sulfide. Now, in this particular one, this is going to be aqueous, and this is actually going to be aqueous as well if we look at our solubility rules. And because they are both aqueous, what that essentially means is you essentially got all these ions just floating around. Nobody's really coming together to make any type of solid, to make any type of liquid or anything like that. You just got pretty much all these solutions flying around or ions flying around. And that really means that in this particular case, not much is going to change. You're really going to get no reaction in this case because of the solubility rules. Any questions on any of those two? I'll put it back up in just one sec. Just want to make sure we are. Oh, we got one more. Any questions on that one? All right. So why don't you try this last one, I think. See what you come up with. So I tell you what, on this one, why don't we do all three, write the molecular equation, the total ionic equation, and the net ionic equation. So take a couple minutes and we will talk about that one. So do all three of those equations, make sure they're all three balanced, and we'll do it in just a second. Okay, so since we're getting to the end here, let us take a look and see how we're doing. So we are taking ammonium sulfate and we're reacting it with lead to acetate. And we know both of these are solutions because they say they're solutions, but just in case, this guy has ammonium, which is soluble in everything. And actually, I don't know if it was on the list, I think it was, but acetate is also soluble in everything. So that's how we know both of these guys would be aqueous. Also can recognize it as a double displacement reaction, as that's positive, that's negative. This is positive, and this guy is negative. So again, here we want to really just take the basic units of each of these guys and put them together. So the basic unit of this guy is ammonium, which is NH4 plus, sulfate, which is SO4 2 minus. Again, not concerned with the little 2 on the bottom. Lead here is a +2 charge, and acetate is a -1 charge. So again, our positive guys will switch partners, and we want to make sure that we start with the correct formulas for each of these. So the ammonium, which is +1, will come together with the acetate, which is -1, which means we just need one of each of those. Then the lead, which is +2, will come together with the sulfate, which is -2. So also we just need one of each of those to get our correct formulas. Again, once we get the correct formulas, then we can do the balancing. So to balance this, we just need to put a 2 in front, and that should do it. In terms of solubility, this is going to be soluble. Again, here we have ammonium, which is soluble. We also have acetate, which is soluble. Lead to sulfate. Sulfate is actually going to be insoluble in this case based on the solubility rules. So again, this would be our molecular equation. We then can write our total ionic equation by breaking apart everything that's aqueous, keeping together, again, things that are solid, liquid, maybe a gas if we come across it. So when we break this guy apart, we get 2 of the NH4 plus. The 2 comes out in front. We also get 1 sulfate, which is -2. When this guy breaks apart, we get a lead that has a +2 charge. And that's aqueous. And the 2 comes out in front for our acetate, which has a -1 charge. Going to the other side, this guy will also break apart because it's aqueous and it's sort of a strong electrolyte. And when we do that, we do distribute the 2 to each of them. So we would have 2 NH4 pluses plus 2 of the acetate. And again, here our solid would stay together. So this again is our total ionic equation. This again is where we're going to look for those spectator ions, which in this case, we have the ammonium on both sides. And again, you can see if you do everything balanced, you should have the same number of spectator ions on both sides. And in this case, we will have our acetate, which is the same on both sides. So again, these are our spectator ions. I'll just write SI for each of them. We're going to cancel those guys out. And that is going to leave us our net ionic equation, which is really what's happening in this reaction. It is the lead with a +2 charge coming together with the sulfate that has a -2 charge. And it is forming lead to sulfate, which would be our solid here. Any questions on any of those steps or calculations? Not really calculations, I suppose. So like I said before, you need to be able to use solubility rules to predict if something is going to be aqueous or solid. You need to be able to write each of these equations correctly balanced and be able to do the molecular total and net ionic equation, and again, identify those spectator ions. So just to wrap up this little part here, the big class of reactions is double displacement reactions. Underneath that big umbrella of double displacement reactions, one type of double displacement reaction is a precipitation reaction, like we're talking about here in these examples. And in a precipitation reaction, it means that you make a solid. Any questions on any of that? All right, we will stop there today, I think. Couple of things. Let's just talk about the future here this week. At this point, we should be able to do the experiment, which is experiment 8. So that technically will be put up as soon as we're done here. It's not up yet, but it will be up on our Canvas site. There's a video for experiment number 8, which is double displacement reactions, which is essentially what we're talking about here with all these reactions. You'll need to watch the video. You'll need to do the pre-lab questions that's in your manual, the data table, and there's no calculations, and post-lab questions as well. So you need to watch the video, answer the post-lab questions, the pre-lab questions, and obviously the data table, and kind of fill in your observations from the video. There is no type report, so this is not a formal report or anything like that. So you essentially just need to fill out all those pages and obviously upload it by the due date. So I think I gave you till the end of the week to do that on Friday. So that one will be due on Friday. You also should be able to now start and do the study assignment. I want to say it is study assignment, maybe D. It should say net ionic equations. Give me one sec. Let me find it for you here. I'm going to stop sharing my screen. I'm still here. Just see which one that is. That is, sorry, study assignment E, as in my last name. So study assignment E, which is net ionic equations, you should also be able to do as well. So these are the 2 labs that you really should be working on this week for sure. You should be working on experiment 8, which is due Friday, I believe is what I put it. Gives you some time. And then also study assignment E, which I believe is net ionic equations, which is kind of what we've been doing here. I'm going to probably make that one due next week. But again, at this point, based on our lecture, you should be able to do both of those assignments. Okay, so in terms of lab, that's sort of what you should be focusing on. I believe you have some that are due today, some study assignments, if I'm not mistaken. And that probably would be study assignment C, I think, and D, I almost want to say. So I think those are the ones that you should have out. That should be like grams, moles, units, and all that kind of stuff. So I believe that is due this week. I think it might even be due today. So make sure that you do upload those as well. Any questions in terms of the labs that's sort of for this week? Okay. So coming up on Thursday, 2 days from now, I guess I should write it, but we are going to have an exam, and that is going to be exam number 2. And again, exam number 2 will be done on our Canvas site, and you will get some more information, hopefully before Thursday's class, but you'll get some more information about how to access it. Let me, best way to do that. I think we talked about what chapters were on that last time. Give me one sec. Let me just find it because I think we wrote all that stuff last time. Just get there. Let's see here. All right, so I believe exam 2 should be chapters. Let's see if I get this back up there. Maybe it'll work or not. Super unhappy with me. There we go. You can at least hear me, I hope. Okay, good. It didn't really like what I just did there, so I will try not to do that again. Let me see if we can get it there, maybe. Yeah, okay, I think you can see it. So again, last time, I think we talked about it, but last time, the exam 2 will cover chapters 3, 4, and 5, which again should be Lewis structures, geometry, polarity, hybridization, nomenclature, and then obviously chapter 5, which should be our grams or moles, Avogadro's number, empirical, and molecular formula. Yeah, I'm going to post experiment 8 as soon as we're done here. I got to open it. It'll be up there as soon as we're done talking here. Experiment 8 will be on Canvas. As soon as I close this down for lecture, and then get a chance to go over there. So within a few minutes after I'm done talking and close it down, it'll be up there on Canvas. So let's talk about the exam really quick before we kind of finish lecture. The exam will be Thursday. What I think I'm going to do is this. There will be no live lecture or lab on Thursday. That will open up the time period for you to take the exam. So the exam will probably be available around our normal lecture starting time, somewhere around 5:30ish. And again, you'll get an announcement to let you know, sort of when it will be available. The exam will be open for a window of time between 5:30 and I'm not sure how much time, but there will be a period of time for you to log into Canvas and to take the exam. A couple of things before you do that is you want to be sure that you are completely ready to take the exam before you begin. So you want to make sure that you have a calculator. You need some paper because there will be questions where you need to show work. So you'll need to be able to show your work. And then when you're done with the exam, you will be expected to upload the work, kind of like how you do your lab reports and so forth. You'll need to upload that work that shows it. The work that you show should show all the units, the setup, the correct answer, hopefully, and all that kind of stuff like normal. You will need to answer the question online as well. So you'll need to input an answer online, and you'll also have to obviously do the work for the written part of the exam. The answer that you put online does need to match the answer that's in your work. If you do not answer a question online, I will not look at your work. So you can't just say, I just did everything on the paper. I don't really care. You need to input an answer online, and then I will double check obviously your work as well. This way, in case you put the answer in wrong or get the wrong answer, if you show the work, I can still give you some partial credit like a normal exam. The exam will be written as best as I could do to make it look like our normal exam that we take in person. So what that means is there will be the first part of the exam that will be all multiple choice questions, just like when we take it in class in person together. For those questions, that is the multiple choice part of the exam, you do not have to show work, obviously. Just like in normal cases, you don't have to show work. You just need to obviously, in this case, click the right answer, I suppose. Then there will be a second part of the exam, just like our normal exam, that is the written portion of the exam. And for that written portion of the exam, just like normal, for anything that has work associated with it, you do need to show all the work. And just like a normal exam, if there's a question that does not have really any work associated with it, you do not need to show the work. Every question that is on the written part of the exam will clearly say in the question, you need to show upload work for this question, or it will say you do not need to show work. So every question that's going to be in the written part of it will say exactly that, one of those two things. Either you need to show the work or you don't need to show the work, okay? Now, let's talk about a couple important things as well. When you go to take this exam, once you start, the timer will start counting. And even if you click away from the exam, which you shouldn't be doing, you go away from the exam or whatever it may be, and you go back to your exam, the timer will continue. So once you start, you want to make sure that you can finish, obviously, because the timer will not stop if you start it. Second, when you submit the exam, the submit button will be at the very bottom of the exam. You will be able to see all the questions like a normal exam. So you could go through all the questions, work on whatever questions you want in whatever order, but you'll get all the questions given to you at once. You could go through it. And again, like I said, work on whichever ones you want to do. And then at the very bottom of the last question will be the submit button. Do not hit the submit button until you have completed the entire exam. Otherwise, you will submit an incomplete exam and the exam will not be reopened for you. If you go to submit the exam before you answer all the questions, it will actually tell you that, hey, are you sure you want to do this? You left like 30 questions unanswered or whatever it is. So hopefully that warning will stop you from doing that, but do not hit the submit button until you have completed every single question that you're going to answer, from the multiple choice down to the written part. Any questions on that? I'll answer your question about the homework in just a second. In addition, when you get that window of time where the exam is available to take, that window of time, for example, the due date or the last moment you could take the exam. So let's say the exam is open from 5 o'clock to 8 o'clock. It'll probably be longer than that, but let's just say 5 o'clock to 8 o'clock, the exam is open for you to take. If you log in at like 7:50, 10 minutes before 8, when you take that exam, the computer will only give you 10 minutes to complete the exam. So you will not get the full time that you are allowed on the exam. So you need to make sure that you log in with enough time that you will not run out of time, and you'll get the full time that you should on the exam. Which means if you start the exam somewhere around our normal lecture time when it begins, you should have plenty of time and you will not run out of time. But if you start like right before that window when the exam is going to end, it will not give you the full time. It will cut you off and automatically submit your exam. So make sure that you start at the reasonable time. It is a normal exam, which means you should treat it like a normal exam. You're not supposed to use anything other than what's provided to you on the exam. You will be provided a periodic table and some conversions like normal. You should not use anything else. You should not talk to anybody or anything like that. And by the way, there are different versions. So just like normal, don't have the right answer on the wrong version. That would not be a great thing either. So you will be able to get conversions and a periodic table will be provided for you. When you go to take the exam will be in its own module. It will give you, there are certain steps that you have to take to actually take the exam. The first step is you will have to open and read an academic honesty agreement, which you can either print out and sign and upload with your work, or there will be an electronic version of the academic honesty agreement that you can electronically sign. Once you do that, it will then actually open the exam for you to take. And then again, make sure that you are completely ready to take the exam before you begin. Once you've taken the exam and submit the exam, if you go back to that module, there will be an assignment there that says upload your work for exam 2. You click on that and you should upload your work. You should upload your work within a reasonable time after you submit your exam. And I will tell you how long you should have to do that, but it should be submitted within a reasonable time, after you submit the exam, not days later or anything like that. Any questions on that? To answer your question about the homework, there will be a separate assignment in the module section where you can upload your textbook homework, much like you uploaded your exam. So please do not email me your homework or really anything. Everything, to be truthfully honest with you, should be uploaded through Canvas, because I'm going to be honest with you, I get thousands of emails already, much like yours. I don't want to miss anybody's work or anything like that. And since everything's sort of integrated through Canvas, it is best to upload everything through there so that you will get credit for everything. So make sure that you do that. So the book homework, like normal, is due on exam day, which will be Thursday. And again, there will be a separate assignment in the module section that says upload exam 2 homework, and that's where you can upload that. Other questions on the exam or anything like that? So like I said, there will be no live lecture. I might do a recording just to maybe finish this chapter to keep us on pace, that I might post up in a few days or before next week that will cover the rest of this chapter. I haven't decided yet, so I'll see maybe if I could do that. But we won't do anything live, so that could hopefully free up the time period, for you to sort of be able to take the exam and not have to worry about sort of anything else. Any questions on any of that stuff? Okay. I will, though, even though I won't be here live, I will be monitoring the exam. I can see who's taking it, how long, all that kind of stuff. So I can monitor the exam while you guys are taking it. If you should run into any problem, which I don't think you should, I apologize in advance. I'm going to write way more instructions as you probably need, but I'm just trying to write instructions enough so I could think of any type of question that you might have. So make sure you do read all the instructions at the beginning of the exam. In each individual question, make sure you read the instructions. And again, I apologize if you feel like there's a lot of instructions, but since this is probably new for a lot of people, I just try to cover everything that I could think of that you might have a question on to try to get those answered for you without having to contact me. If for some reason you do find something that is unclear or something like that through Canvas, you should be able to email me, and I will be available through email during that period of time. And I will get back to you pretty quickly, while you're taking the exam. Just like normal, I can't answer the question for you. I can't tell you how to do the question. But if there's something that's unclear or something like that, or you feel like you're missing something, you can contact me. Clearly, you should only contact me through Canvas. You shouldn't, be surfing around on your phones or anything like that while you're taking the exam as well. Any questions on anything? Okay, so again, I apologize for running a little bit late here. Do keep an eye out on Canvas and also your email tomorrow and early on Thursday, because there will be some instructions coming your way in terms of the exam and how to access the exam, and there'll probably be some online exam instructions, which I think are up already for kind of that makeup exam that I did. So if you want to kind of look at them, that's sort of the same process is going to occur. The times and dates are different, obviously, but you could look at that if you want already. That's in Canvas. So I'm going to stop the lecture now. I'm going to take me a minute or two, and I will make visible experiment 8. And since I ran a little bit late, maybe take 20 minutes, 25 minutes, and then I will open up the lab section in case you do have questions. If you want to come and ask about the labs, or I guess you could ask about anything in terms of the exam coming up and stuff like that. So for this week, you should be focusing on experiment 8. You should also be focusing on study assignment E, which is net ionic equations. Experiment 8 is officially due on Friday. And I think study assignment E will be due sometime next week, early next week. And again, you do have, I guess, those couple of study assignments that are due today, I believe. So make sure you upload those if you haven't done so already. Any other questions before we end the lecture part? Again, the lab part will start probably in about 20, 25 minutes. All right. Have a good one. I'll see you next live in lab if you're coming, but if not, next week.